this. It's a real pleasure. Let me start. I'll make sure I can share my screen, get some slides up, and we'll be off. So, um, as Alta indicated, this talk will be a little bit different than your usual science seminar. It's largely based around the talk that I give to the public around the topic of this book. And so forgive the generalizations and some of the sort of pop sci language that I'll be using, but hopefully it'll still be stimulating and a bit entertaining. And then I've thrown in a few somewhat more technical slides towards the end of the talk to keep us interest up. So the book and this talk is really centered around a quite simple question that I think is an astrobiological question, but it's not one that I believe we ask that often. And so part of the idea of the book was to explore this in a fairly thorough and broad fashion. And so the question is, what happens when life moves beyond its planetary origins? And that's something that we tend to think about in terms of rather parochial ideas to do with our current efforts to explore space, the sort of commercial efforts, the geopolitical side of space exploration, and so on. But I would argue that it is a valid astrobiological question. And it's very interesting to look at it through the lens of astrobiology. And that's what I'll try to give you a little bit of a taste of in the talk today. So I think it's good to remind ourselves of just how much space exploration has taken place over the last 70 or so years. And so, we can do this by sort of thinking about some of the sum total of our expeditions beyond the Earth. And it's pretty extraordinary. So to date, there have been over 140 lunar missions, and that, of course, includes many attempts and failures, but I still put them in here just to give a sense of the scale of the enterprise. There have been over 50 Mars missions, including all of those attempts. Over 700 individual people have been into space, including suborbital flights. There have been more than 3,000 Earth-observing satellites of one flavor or another since the beginning of bona fide space exploration in the late 1950s. There've actually been well over 100 space-based telescopes to observatories, not focusing on the Earth, but looking out into the solar system and the cosmos beyond it. There, in fact, have been 15 missions returning extraterrestrial samples, and that, of course, includes all the efforts that were undertaken during the Apollo missions and that era. And right now, there are some 45,000 identifiable human-made objects orbiting the Earth. And that includes functioning satellites, defunct satellites, and larger pieces of launch systems and other stuff that has ended up in orbit around the Earth, at least for the time being. And we've all heard of space junk. And right now, there is at least 140 million small objects. So that's things of the scale of sort of centimeters or so orbiting the Earth as a consequence of our efforts to place stuff into space. And that's a whole other discussion about space pollution, both in orbit, but also during the re-entry of junk into the Earth's upper atmosphere. Right now, there are some 36 active solar system missions. That includes those on planetary surfaces like Mars or the Moon. And of those 36, in fact, 9 are active missions at Mars today. And again, I'm giving this to you as I would give it to a public audience. The idea is to get across the sheer amount of space exploration that has taken place over the last 70 years. It is kind of extraordinary. And it seems to be carrying on, and if anything, accelerating, because there is now near exponential growth in the number of objects being launched into space. And we can look at that data from various sources. There's a wonderful website called Our World in Data, where you can get to numbers on this and many other things. And this graph is derived from data there, and it shows the number of objects, satellites, probes, landers, etc., being launched from the Earth into space as a function of time, starting in 1957. And it's pretty obvious there's been an astonishing acceleration of that, an exponential growth of that in the last decade or so. Now, of course, much of this is being driven by the effort to place these constellations of satellites into orbit around the Earth, and that's being driven by commercial interests, and many of those commercial interests are in the United States. But it's not confined to the US. There's an increase in the rate of launch from across the world, other countries, other space enterprises. And while this is the number of objects launched into space, and many of them are launched, in big batches on single rockets, if you actually look at the statistics for launches themselves, there are now some 30 viable launch sites around the world, and we're close approaching the time where there will be a rocket launch to space roughly once a day from somewhere on the surface of the planet. So this is all very interesting. And if we try to step back as astrobiologists and look at this with a broader perspective, it raises some interesting questions about, what is that perspective? How should we be evaluating this as a phenomenon happening to the Earth? And my feeling on this is that it's valid to think about the natural history of space exploration, much in the same way that we think about the natural history of life on the Earth. And the natural history of space exploration is interesting because I think it too, much like the history of life on Earth, requires going back to essentially the origins of the Earth, the origins of this place from which there is now this new phenomena of stuff being launched into space. And the major planets, as they condensed out of a molecular cloud somewhere in the galaxy, that underwent gravitational collapse and all the complex processes that followed from that. 4.5 billion years ago, the major planets are in the sort of final stages of formation. And of course, our interest lies in the third planet from the sun, this planet that we've ended up calling the Earth. And the history of the Earth, as most of you listening to this talk are very much aware, is itself an interesting and complex thing. The Earth has taken on many different forms, many outward forms, over the last 4 billion years or so, and it has undergone very significant evolution. Some of that evolution has, of course, been driven by the rise of a biosphere, the rise of life on the planet. So some 4 billion years ago, the Earth was perhaps more of an ocean world with shallow oceans spanning the planet and perhaps very little, if any, continental landmass poking above the surface of the water. Its atmosphere has undergone significant evolution over time, starting from the primordial atmosphere left during the final stages of planetary accretion to this remarkable change induced by the rise of molecular oxygen in the atmosphere over an extended period of time. And of course, that rise in molecular oxygen has been driven by the rise of oxygenic photosynthesis on the planet and the mineral properties of the planet and all the feedback loops that go into setting the final concentration of oxygen in the atmosphere. That oxygenation has, of course, also modified things about the Earth's climate stability by modifying the atmospheric chemistry, modifying the ocean chemistry. And we believe that at certain points in the deeper history of the Earth, that may have given rise to these so-called snowball Earth events, these global glaciations, where there may have been significant ice cover all the way down to very low latitudes. And the global mean temperature may have actually been below the freezing point of water, below 0 Celsius. And then over time, the Earth has come out of those glacial periods, those snowball events, and continued to evolve with movement of continents and ocean configurations over time, further changes in atmospheric composition and variations in atmospheric composition back and forth from certain states with more or less oxygen, more or less carbon dioxide, and so on, until we reach the modern Earth. But there is something that is common across this entire history of the evolving Earth, which is, from a thermodynamic point of view, the Earth has tended to be very closely approximated by a closed system, meaning that there has been very little exchange of matter between the Earth and the surrounding universe. Yes, there has been atmospheric leakage. Yes, there has been infall of interplanetary dust and meteorites and the occasional significant asteroid impact. But on average, over billions of years, you would consider the Earth to be a thermodynamically closed system, which is important for understanding of past climate and understanding of the Earth's biosphere and so on. However, I would argue that something new is happening, something really interesting is happening that makes the Earth a far less thermodynamically closed system than it ever has been before. And that new thing, of course, is the rise of a species that is now seemingly undoing some of the accretionary processes that formed the Earth in the first place. So this little animation, um, hopefully you can see that okay as it streams down Zoom here. It's an animation, greatly exaggerated animation, but based on real data of the progressive increase in the number of objects that have been purposefully placed into orbit around the Earth, starting in 1957, moving up to modern times. Each little moving object here is meant to represent an actual satellite or space launch, um, hugely exaggerated so that we can actually see these objects. But the intent is just to give us this visual representation of this rather strange and extraordinary thing that's happening to the planet. It seems like it's undoing itself. It's an anti-accretion taking place. It's now actually spitting out pieces of itself into space in a way that has not happened before in the last 4 billion years, in a way that makes the planet far less similar to a thermodynamically closed system than it ever has been before. And that isn't just restricted to the near Earth orbit. Again, through the lens of astrobiology, looking at this as a phenomena taking place in this planetary system, uh, those pieces of the Earth have been sent out across the solar system over the last several decades. They've been sent into orbits around the sun. They've been sent into orbits around all of the major planets, or visits to major planets, many of the major moons of the solar system. And now, of course, there are a few of those small pieces that are heading out into interstellar space and have already crossed through into what is now largely the interstellar medium towards the outer reaches of our solar system. So this is a very remarkable phenomena that is underway in our planetary system at the moment. And if you were to scrutinize as a sort of objective alien scientist looking at what's happening in the solar system, if you were to scrutinize those pieces of ejected material that are seemingly being shed from this planet, you would find that each of them is extraordinarily complex. They're not simple mixes of the elements that are found on the Earth. They're actually very complexly structured and configured objects with, of course, solar panels and spacecraft buses, and they're complex down to a microscopic scale because of things like electronics. They have exquisitely etched and sculpted silicon-based devices for performing digital calculations that are truly microscopic in scale. So these are very, very strange things for a planet to be shedding into the universe. And the shedding of this material, this anti-accretion, is not just a one-way um, process. It's not just a one-way influence into the surrounding universe. I would argue that the shedding of these objects and the information they have gathered and returned to the Earth actually now connects the Earth and the life that inhabits the Earth to other places in the solar system in a way that has never happened before. So obviously we now have the ability to study and observe places like Mars in extraordinary detail. We have familiarity with the landscapes on the surface of Mars. We have familiarity from the orbit of Mars, of the landforms, and even at a microscopic level, We have familiarity with the mineral formations and concretions and so on that exist on the surface of Mars. In this sort of philosophical standpoint, it's a connection between two worlds and, of course, between other worlds as well that simply hasn't existed before in the last 4 billion years of the history of the Earth. So this is a really interesting phenomena to try to understand. And given what's happening right now with the surge in the number of objects being placed into space and everything that has been happening over the last several decades, I would argue from this grand perspective, this sort of astrobiological perspective, that what we're seeing is a major transition in the history of the Earth and, of course, also in the history of life on Earth. And transition points in natural history are really interesting. They're not just about change, they are about changes in what is possible. So to go back to the example of the oxygenation of the Earth's atmosphere, as you all know, the oxygenation of the atmosphere and the availability of molecular oxygen created new possibilities, new options for metabolism on the planet. And that metabolism also opened up new chemical energy sources and mechanisms that greatly amplified the capability of life on Earth. You know, cells that utilize oxygen respiration can express many more genes from the genetic code that they carry and so on. And it gives rise, we think, to the options for multicellular life because of that energy density that's available through oxygen. So the oxygenation of Earth's atmosphere was a massive transition. It was a very protracted, prolonged transition, but it ultimately it changed what would be possible in the future. And I think the same is largely true for mass extinction events, which of course remove many organisms and species from the mix. But in doing so, mass extinction events tend to create new environments and also new open niches into which life can move and undergo evolution through selective processes. So there too, a major transition like a mass extinction doesn't just change things, it changes what is possible. And I think that is the way to try to think about space exploration and its implications. So because this is a partially pop sci talk, it's helpful to try to lead the audience through this using stories and using parallels. And I think there's a really important and interesting parallel in a very particular story that is to do with this ship. So this is the HMS Beagle, as it was in 1831, around the time that it set out on a 5-year voyage around the world. And of course, as you know, one of the crew members on the Beagle was this person, a young Charles Darwin. And this voyage on the Beagle, I think, gives us a number of insights as to how a species like humans can induce massive transitions in the history of life, not through enormous changes enacted in the physical world, but actually through gaining understanding, gaining knowledge about the world, and gaining knowledge about the universe around us. And that parallels what I would argue is happening in space exploration. So let me step through this a little bit. So I think there are two really important parallels between the voyage of the Beagle and space exploration that are useful to think about. So the first one is kind of mundane and simple, and it's really just about the mechanics of exploration. So the Beagle really paralleled much of what we see in modern spacecraft and space exploration in a number of ways. So the Beagle was this highly customized vessel. It was an older warship that was modified over time. And for this particular voyage in 1831, It was massively customized using all the latest technology. So it had copper plating placed on the ship from the masts down to the hull to divert lightning strikes. They replaced the iron cannons with brass cannons to try to mitigate the impact on Earth's magnetic field and the ship's compasses. They even carried 22 chronometers on board, 22 timekeeping mechanisms, because knowing the time relative to an absolute datum, which would be the Greenwich Mean Time in England, was of course essential for navigation at the time. It was how you determined your longitude by knowing the local time compared to a datum and making astronomical observations or observations of the sun and the moon and so on. So it had all of these very innovative features in this vessel, and it was necessary because this was setting out on a planetary voyage. This was the equivalent of a true piece of planetary exploration, planetary voyage, or interplanetary exploration in the 19th century. The other piece of this is to do with what happened to Darwin and his ideas as a consequence of being on this expedition. And I think the closest um, parallel to that, to the space exploration for Darwin's experience, was he he had an overview effect experience. So astronauts talk about the overview effect, which is when you're in orbit around the Earth, you gain this sense of the unity of the planet, the fact that it is all one system, the fact that there are no actual boundaries between countries, those artificial constraints brought by humans. And I think Darwin very clearly had a similar sort of experience, although rather extended over the 5 years. He was exposed to a variety of environments and species that he had not been exposed to before, and he began to see them as all part of the same system. And I think that was a truly remarkable aspect of this voyage. And of course, as we know, much of what he saw and learnt and absorbed during this voyage would later help support him as he put together his ideas on the origin of species and the idea of a mechanism of evolution through natural selection. And that came from many pieces of the voyage, but also his later work as he assembled the theory. But we know that things like the finches on the Galapagos Islands played some role in sculpting and carving his thought processes, because here he saw species that were clearly very, very much the same in some ways, but also very different. And he began to understand that species are sculpted by their environments in ways that can perhaps be evaluated and coalesced into a single unified theory of the origin of species and the nature of biological evolution. Now, all of this came about because of this exposure to new knowledge, this exposure to data gathered from across the world, and that was enabled by technology and, of course, his own training. And I would argue, and I'll get to more of this in a moment, that that really parallels what's happening with space exploration. But there's another really important point here to do with this idea of transitions that create changes in what's possible in the future. Because I think Darwin's eventual theory of evolution itself caused change in the world. It caused an evolution of evolution. It changed what was possible for evolution in the future. And we can think of this in a number of ways. So, for example, following Darwin, there was an effort and an urgency to understand the physical basis of evolution. In fact, the molecular basis of inheritance and change. How is that happening? And that led to the discovery of the molecules of DNA and RNA and their structure and a fully fledged sort of biomechanical theory of how this all worked. And that changed our behavior. That changed how we behave about our own inheritance and health. It changed our approach to dealing with, uh, food stuff in terms of plant life and animal life, and how we make decisions in the world to try to steer things in directions that we want them to be steered in. And part of it comes from this idea that evolution is at play. And of course, discovering the molecular basis for evolution has led to modern tools like gene editing tools, which very much change the nature of evolution. They change what is possible in evolution on very rapid timescales. And that all stems from Darwin's earlier work and in part his voyage on the Beagle. And things like gene editing change our actions in the world, and if it changes our actions, it therefore will impact all life on the planet. And I would also argue that the ideas of evolution that Darwin put together are actually at the root of many of our modern advances in AI and machine learning, which is what this little diagram on the right-hand screen of the screen is meant to show. You know, modern AI, statistical AI, deep learning, large language models, all of those are based on a much deeper sort of philosophy or understanding of the nature of change in the world, of feedback-induced change, of selective forces that act to modify things towards more optimal solutions. That is how we do machine learning. So I would argue that Darwin's experience on the Beagle, his eventual construction of a theory of evolution, didn't just change our understanding of the world, it changed our behavior in the world and therefore changed the nature of evolution itself. And I think space exploration is the same kind of thing, is doing that and has the potential to do that down the line. And for space exploration, I think it even goes back further than something like biological evolution, because I would argue that it was the trait of thought, of analytic thought, that really enabled life to break free of its planetary origins. And that's to do with the requirements of getting from the surface of a planet into space, the energy density requirements, and so on, are not at a level that biology seems to home in on. You need to be able to think your way out of the problem. And this goes back a long way, thousands of years, to ideas such as the idea that there is this thing we call nature. There is a physical reality that has distinct properties. It doesn't exist just in our head. It is a reality outside of our minds. And the ideas of cosmology, which is about the structure of that reality, and ideas about the nature of motion and the recognition that there seem to be universal rules that apply to this thing that we call motion. And those universal rules include things like forces, a concept that helps us explain how motion changes and evolves over time. Concepts like momentum, which is a property that we can assign to all matter in the universe, and the property that we can assign to this phenomenon of motion to better understand it. And with momentum, quantities like momentum, come conservation laws. The observation that momentum summed in a system tends to stay the same over time in non-dissipative systems. And that also applies to this property, this quality that we assign to parts of the world that we call energy, which is about the tendency of things to happen in the world, or the potential for things to happen in the world. And there too, there is conservation of energy in systems. And eventually, over time, all of these considerations and observations of the universe around us gave rise to ideas about this thing we call gravity, the tendency of matter to attract other matter through a force of some kind. And that gave rise to modification of the idea of laws of motion into a more general form that we would call orbits and their various families. And that's related to these more sophisticated ideas of least action principles. Why do things tend to move in straight lines or roll a certain way when they're rolling down a hill? And all of that culminated in the early 20th century with deep mathematical work and ideas about the nature of symmetries in the world. And it turns out that things like the conservation of energy is a consequence of symmetries in time. It's literally a consequence of the fact that physics today is the same as physics tomorrow, at least as far as we know. All of these things to do with human thought and a construction and abstraction of the world around us were essential for life to be able to break free of its planetary origins. And on top of that, you would add this certainly human quality, and maybe other species share it to some extent too, this human quality of imagination, of an ability to abstract, an ability to extrapolate from the known to the unknown and ask questions about what if we do something? What if we try to get to the moon or elsewhere in the solar system? It's really, really fascinating. Now, just like with Darwin's evolution, the theory of evolution, space exploration has and is hugely impacting life on Earth. It is doing that through us, but that is the same as many other things. So through our ability to navigate, to communicate, to study changes in the land composition of the Earth through remote sensing, understanding plant health through remote sensing, tracking other species from space, understanding the nature of the sun, its variation, understanding the nature of other planetary systems in or other planets in our solar system all give us greater insight to the functioning of the Earth and changes our actions on the Earth, our decision points, whether they're to do with the nature of weather or the nature of climate and the nature of other species and our requirements for food and health and so on. I would argue that reaching out into space, being able to place devices in space, to study the Earth from space and to look further afield, have all profoundly altered not just human civilization and human behavior, but through us, change the environment for all life on Earth. So I consider the the expulsion of life from its planetary origins as a major transition point in the evolution of life and a change in what is possible in the future. And I think there are some hints of some pretty dramatic changes that may come later in time, but may come at a pace that's quicker than we might have imagined. I would say that there are hints of an emergent reshaping of the solar system already, not just a reshaping of the Earth as it sort of expels pieces of itself out into space, but in other places as well. So even on Mars, the tracks left by rovers on the surface of Mars may seem inconsequential, but they are a reshaping of another world. And who knows what, erosion processes will be set in motion by those tracks over the coming centuries and thousands of years. Things will happen on Mars that would not have happened otherwise. We've also constructed these habitats in space, these sort of mini biospheres that didn't exist before. That is a reshaping of the solar system. And one of the most dramatic examples of an emergent reshaping of the solar system is one you're probably mostly familiar with, which was back in 2022, the DART mission to attempt to modify the orbit of the asteroid Dimorphos, which is itself in orbit around another larger asteroid. That was done through impacting the DART spacecraft onto Dimorphos. And in fact, just last week, data was analyzed to show that the orbit of the entire asteroid system, both Didymos and Dimorphos around the sun, was modified. So the orbital period around the sun changed by about 150 milliseconds due to this impact. And at the scale of the binary asteroid system itself, the orbit of Dimorphos, the orbital period around the larger asteroid was modified by about 33 minutes. And we know that material ejected from this collision has now sailed out beyond this dual asteroid system. And some numerical work suggests that that material in a few thousand years will cross the orbit of Mars. And in fact, there could be a meteor shower in 4 or 5 thousand years' time on Mars that is a direct consequence of human actions thousands of years earlier when we crashed this spacecraft into Dimorphos. So these are all hints of something really, really profound happening in our solar system. Okay, let me try to. I have a couple of more technical slides, and then I'll get close to wrapping up. So one thing that is interesting about looking at the nature of space exploration through this astrobiological lens is it starts to make you think about other ways to characterize or conceptualize planetary systems. So obviously in astrobiology, we are pretty familiar, or most of us are very familiar with ways of classifying um, planetary systems according to things like the circumstellar habitable zone, the orbital range where an Earth-type planet might have a temperate environment on its surface, or indeed zones further from the star that are where objects can be colder and you can have icy moons with interior oceans and so on. And we've used techniques like the calculation of the circumstellar habitable zone to try to evaluate the likelihood of habitable planets for exoplanetary systems, but also studying the history of our own solar system and the history of life on Earth through this lens of very long timescale climate change and so on, which is connected to the circumstellar habitable zone. Well, I would argue that that is fine for when life is restricted to its point of origin. But what about systems where life is no longer restricted to its point of origin, is doing what we're doing, which is beginning to spread out, beginning to disperse across its planetary system? It gets interesting because there are other things that you need to begin to consider then to ask how well a planetary system can sustain interplanetary life. So you need to worry about stellar activity and solar storm risk. You need to worry about cosmic radiation, to worry about orbital movement. How do you get from one orbit to another? How easy is that? You worry about solar power. You worry about things like resources in asteroids in our own solar system. That's an important factor, and so on. And after writing the book, I found myself getting more and more interested in this. And so just a couple of slightly more technical slides. I put a paper out recently. It's a preprint. It was submitted to the Astrobiology Journal on this idea of an interplanetary habitable zone. So again, this is thinking about life that is moving beyond its planetary point of origin. How do we assess the capacity of a planetary system to sustain that sort of life, much as we think about the habitability of an individual planet? Well, without going into too many details, I think in a fairly agnostic way, without saying too much about how a species is becoming interplanetary, whether it's through technology or some unknown biological traits that we've yet to think of or understand. It comes down to factors that are not dissimilar to those that we use to evaluate the circumstellar habitable zone, but they're articulated slightly differently. So, for example, there are things to do with the cost of existence. So, costs of existence for interplanetary life is to do with delta V, or energetic costs for orbital transfers and ascending or descending planetary surfaces. It's to do with risk or damage. So there's stellar and cosmic radiation, which are connected to each other because of the way the heliosphere modulates the incoming cosmic radiation, and that in turn is related to stellar activity, solar activity, and so on. And then this idea of reward, that to exist, life needs power and materials, and so whether it's technological or biological. And so you have to think about the resources that are available to support life and interplanetary infrastructure, supporting life, but also supporting the needs for fuel to get around, the needs to build structures, and so on. And it's kind of a fun exercise. It's a little wacky. I'd be the first to admit that, but it's been sort of fun exploring this. And in the paper, I go into this in some detail, and you can construct, I mean, the different ways to do this, but you can construct a numerical metric that incorporates these things like cost, risk, and reward into a series of factors that you can add together or subtract to come up with a measure of an interplanetary habitable zone as a function of orbital radius. And I realize these plots are probably a little hard to see, but the upper plot is an example of making this calculation for the solar system, starting with Mercury, Venus, Earth, Mars, asteroid belt, and so on. And the bottom plot is trying to do something similar for the TRAPPIST-1 exoplanetary system with a lot of assumptions, right? Assumptions about resources and so on. But you can see that the functions look very different between the solar system and the TRAPPIST-1 system. And in fact, part of the conclusion of the paper is a system like TRAPPIST-1, which is of great interest because of the number of planets and the potential of some of those planets to be in the classical circumstellar habitable zone. But actually, for an interplanetary species, it may be far less good as a place than our own solar system. It may have a lower interplanetary habitability overall. Modeling this is complex, just like modeling the circumstellar habitable zone often requires you to eventually go to more sophisticated climate models for planets and models of planetary chemistry and radiative processes and so on. And for this interplanetary habitable zone, I actually found that perhaps the best way to do this, or the more complete and accurate way to do this, is to model it as a dynamic process. And it's a dynamic process that I've modeled using agent-based simulation. So this is where you have a population of little agents. They each follow a rule set in order to make decisions about where they're moving, what they're doing at any given time step, and so on. And you essentially let them loose across a planetary system. And so this is just one figure from the paper. Again, I won't go into it in much detail, but the upper graph shows the growth in the number of agents they're allowed to replicate when conditions are correct, and they're allowed to move around, and they make decisions on when to move and where to move to based on all of the factors I mentioned before. And so in this particular plot, it's modeled over about a century, and everything starts out on the Earth. The population of these interplanetary agents grows over time, and at some point they begin to populate the moon, and at some point after that they begin to populate Mars, and then eventually the asteroid belt, and so on. It's kind of fun to do this, and the downside is there are many parameters that need to be tuned, tweaked, played with. But I think that's also true for computing circumstellar habitable zone. And so it's not so very different. It's just we haven't really done this kind of thing before. And of course, you can make the same kind of models for other planetary systems like the TRAPPIST-1 system. And the paper does that and again shows that the TRAPPIST-1 system is perhaps surprisingly seems to be far less suitable for an interplanetary species in terms of its capacity to sustain that population. So I think this is kind of an interesting offshoot of you write a popular science book and then you have these ideas that you then go and look at later on through a more technical lens and hopefully do something useful with it. Okay, let me get to the last couple of slides, and we're sort of going back to sort of public audience style presentation. So, how do we really conceptualize this idea of what happens to life when it moves beyond its point of planetary origins, the original question that I posed at the start of the talk? Well, I found myself needing to call it something, and especially for a pop sci book, it's good to put labels on things that people can grasp. And so I ended up calling this phenomena dispersal. And dispersal is a useful word here because it captures what I think is really the underlying key dynamic is just the idea that life is dispersing itself into a new landscape, into a planetary system, much as life has dispersed itself around the Earth. over time and continues to do so when life moves, species will move into a new environment and so on. And when you think about it this way, it raises some possibilities for sort of back of the envelope calculations that help kind of bound the problem. Because part of the idea of dispersal is that the landscape of the solar system is so dramatically different than the landscape of a single planet. The scale of the solar system and the scale of its resources are far beyond anything that life on a single planet like the Earth has previously engaged with. It's literally off the scale compared to what life has been exposed to before. And so you may laugh at some of the numbers here, but it's sort of a fun exercise. It's very hard to predict the future. It's very hard to predict exactly how things play out as life becomes interplanetary, but you can put constraints on the problem. You can put boundary conditions on the problem. Maybe this is just my background as a physicist speaking, but I think it's a useful thing to do. And it's kind of fun. So, for example, let's take our solar system. We know something about the number of asteroids that are dispersed within the realm of the major planets in our solar system. We know about their abundances to within some error bounds, and we have some idea of the range of composition of those asteroids in terms of elemental composition. And with that information, you can actually do a sort of back of the envelope calculation and say, well, suppose you could harvest all of the asteroid material in the sort of in amongst the major planets of the solar system and convert that into biospheres, use that to grow life. Well, it turns out there's enough material to grow or form about 6,000 Earth-sized biospheres, which is pretty extraordinary. And if you take that further and say that a biosphere, an Earth-sized biosphere, is required to support a certain number of humans, a few billion humans, it means that in principle, the solar system and the asteroid material in the solar system can be used to grow something like 50 trillion humans and sustain them. And there's plenty of energy for that, plenty of power. All of that would be powered by less than 0.0003% of the sun's total output. Now, that's all outrageous and, the sort of stuff that gets you in trouble if you say it to the press. But it's interesting, right? It is a valid boundary condition, an endpoint, if you will, one endpoint for life that becomes interplanetary. It's not going to happen anytime soon, but it does put some constraints on the problem. Okay, my last slide. Sorry if I've run a little bit long. What are the real consequences beyond growth in number, growth in the amount of biological organisms in a planetary system when life goes interplanetary? What are the consequences for life? Well, I think here's where we sort of come back to some of Darwin's observations. And what we know about life on Earth is a good analog for what may happen out in our solar system. So this is a beautiful animation flying over the Galapagos Islands. And Galapagos Islands already present us with one good example of how when life moves into new niches and is dispersed across a variety of environments in the Galapagos archipelago, it undergoes dilution. So individual species are diluted because different individuals may end up in different places, and that can give rise to later speciation and diversification, or adaptive radiation, to use the evolutionary biology term. And I would argue that that is likely to be a phenomena that also would happen to life that goes interplanetary. And again, in the pop sci mode, I like to end by saying I think this is a remarkably hopeful thing for us, for life on Earth, because maybe a fix for the problems that we seem to be constantly coming up against and constantly unable to solve. Maybe part of the fix is that we need to be diluted. We need to be spread across a much larger landscape, and that dilution will cause diversification. It will change us It will change what comes after us. It changes the possibilities for the future. And I think that's a very positive thing. And it's a counterpoint to some of the um, typical and completely understandable reactions to space explorations being something too expensive and too distracting for us to really spend time on as a species. I would actually argue that it's incredibly important because it provides the possibility of new options in the future in a way that nothing else really does. Okay, I will stop there. I will stop sharing my screen. Thank you so much. I'm sorry if I ran a bit long.